Hi, welcome back. So today's topic is on really kind of a bread and butter. Hi, and welcome back. So today's topic is a really foundational one for any data scientist or machine learning kind of role. It's how to set up your training for models, how to divide up your data, how to analyze how to prepare your data in a way that you can be sure of the results and validate them so that the predictions and classifications or results you're getting out of your model can be trusted, which is very important. So it's really an important task that you need to So today's topic is really another foundational part of data science or machine learning practitioners, being able to prepare and divide your data up in a way that you can trust the outputs that your models give you and train them in a way that lets you be confident of the results. So if you'll remember where we are in the course, we're still in this first section, understanding and preparing data. And the last part of that is this section on experimental methodologies. We talked about what data is, what types of kind of data cleaning and manipulation you can do to kind of set things up so that you have the chance to learn and fit models properly. But there's another task which is not about the data itself, but the way that you treat it. So in more detail, this section talks about how we're going to divide the data up. What are you really training on, and how can you demonstrate and be sure yourself that you've looked at the right portion of the data and that the results you get are something you can trust. So there's a bunch of different methods and really kind of protocols or methodologies for how you do things. Some of them are not strict methods that you can just run a script of. They're really just the way you have to organize everything, and some of them are actual programs or functions you can call to get a certain calculation. So in this section on training and error estimation, we just highlight a bunch of these different methods which you can use, which is like I'm talking about how you divide your data up. So why do we have to think about how you divide your data up? So look at what we're talking about here. We're going to have some function or program that takes in all the data we've been talking about, whether they're numbers or images or text, and we want to output different kind of useful predictions. It could be a prediction of numbers that's going to happen next, like COVID infection rates, or a classification about whether those blobs of pixels in the image are pedestrians or not, or whether this spike in the signal of your time series is unexpected or normal. These are all kind of decisions or function responses that you could give, right? So one fundamental concept here is if you train a model on some data, or on all your data, say, you could possibly learn and fit that But how will you know if your model is correct? How will if you know your model will generalize or be useful beyond the data I actually just gave you, right? So if I give you all the COVID data from the past and you train it and give me some kind of wonderful prediction, how do we have any confidence that it's going to work on tomorrow's data, right? If we assume the past is a good predictor of the future, then we hope it will always work. But that isn't always the case, right? It could be that we were just lucky up until now, or unlucky, and tomorrow things will suddenly change. That doesn't really hold very well with COVID, but in some data sets it might, especially if you don't have that much data. So these training methods are all approaches basically for using some of your data for training and some of it for validation and error estimation, right? So resubstitution is saying that you use basically all your data, as I was saying, like kind of naively just use everything, and you use it for the same data for testing, right? So you train it on all the data I give you, and then you test it and say, well, here my accuracy is 98% on the data from all the COVID from the past, and you just use that. Now, if somebody was using that and giving you that result, you should be suspicious, right? Because that might mean that they're just being lucky based on the past data they have, right? Or that they're tuning it. They can go in by hand and make it predict things very well, but they're not predicting anything they haven't seen before, right? So if you think of a machine learning or data analysis program as a function that can learn mappings from inputs to outputs, if you have enough control or variables in that, you can learn anything, right? And just memorize everything. So if you're just doing this approach, then you'd be very suspect and prone to overfitting to that. So another intuitive method, we just say to hold out half the data. So we're going to take half the data for training and the other half for testing, right? And then hopefully those two sets are independent. Maybe even do it a little bit randomly. The problem is very pessimistic, and it depends on how much you do. Like, why half? Why not, 80% for training and 20% for testing? Why not 20% for training and 80% for testing? How do you know which is what is sufficient? And actually choosing this number is tricky, and that's what the other methods and a lot of people's kind of science and experiments are about. But 50-50 is not very good because it's completely arbitrary, and usually you need much more of that data, right? So you're actually going to be closer to this point where you say most of the data for training and a little bit for tests, and that might be sufficient. So what we're really talking about here is saying that we need to be able to determine which data we're using for testing and training, right? So we say we're going to be learning some model. It's a function f that's going to be going from x to y, and x is our input data, and y are the output label or prediction that we want, right? It's the thing that you want, right, to get. And another way of thinking of it, this is the question, and this is the answer. So we have our data set is size n, right? We have n data points, and the data points are, as we've talked about before, so they're literally a bunch of features that describe it in some way. There could be information about the population, and then there's information about, there's a row for each individual in your data set. And these could be people and their age, career, education, or they could be data points in an outbreak, or they could be genes, or diseases, and these could be genes. So the n is how many data points we have, right? And the question is, what are we training on, right? Are we training on all the data and testing on all that data? That's what this method is. Holdout method, we're training on half the data and testing on half of it, which is also not very good, right? This is biased, right? This is inefficient. Leave one out. We're saying let's take almost all the data and test on one, right? But we'll do this n times, right? So this is also inefficient, but at least it works. Right, and so the idea there is that you train the classifier on almost all the data, and then you test it on the one data point you left out, right? And you get an unbiased estimate there on these, but it could be huge variation because you're going to learn every particular data set, right? So if we have a huge number of data points, one of the trainings for us to do that is we're going to train it on all the data and test it on that one. And another one, we're going to train it on all this data and test it on that one, right? And so you'll get very different answers because the mean of all these points are kind of near each other. But once you include these points, you get a very different response. So the variation between the answers you're going to get and how good they are is going to be very large. So that one's not great, but it leads us towards the one that is kind of great. And that's k-fold cross-validation. This is your default one that you should always use. And the idea is similar to what we just talked about, but instead of one fold, leave one out, you have k of them, right? So in this approach, we say that we're going to divide the data into, we're going to train on n minus n over k of the data, and then we're going to test on n over k of the data, right? And we'll do this k times, right? And this is less biased, more efficient. Right, so why is that? How does that work? We have our data, right, going from 1 to n, and we'll say that k equals 5. 5 is a good way to do this, and so we often call this then FiveFold cross-validation. Right, so the k, you just replace it with whatever the actual number is. So 5, so we need 4 lines, 2, 3, and 4. Right, so there's k boxes, and so each round we're going to do these many times, and we're going to train on all the different combinations of that, right? So we'd train on some of them and test on others, right? And so you train on A, B, C, D, and test on E. And you train on A, C, D, E, and test on B. And train on C, D, E, B. The order probably doesn't matter, etc. Right? And so you do all the combinations. Which one am I missing? B, C, D, E, A. Well, we should have D over here. Right? So A, B, C, E. Oh, there should be one more. So I've only done 4 of them. Right? And so you've got 5 combinations, and you're basically dividing them up that way. And this gives you, why do we do this? So think about why you would do this. Right? When we were doing the one-fold cross-validation, we were like having a little sliver of points here and hoping that this one was a good representation for all that, right? But that isn't necessarily very likely. Here we've got a good 20% of the data set being our test subject, and the other 80% is what we're training on, right? And we're doing that 5 times, and so that gives us the bias, the variation. Because it could be, like, think about why we're doing this. You know, maybe it just happens to be that C, the ones that are in C are easy, and the ones in E are hard, just because of demographics or data or random distribution, right? And you want to average that out. So that's one way to do it. What's another thing you could do on top of this method to help that? Can you think of it? A very simple thing. What order would we be doing this? How are these divided lines happening, right? We've got some data points coming here. So an additional thing you should always do here, I don't know if I have it in the slide, is first, if it's appropriate, some data sets maybe you can't do that, but almost always you can, randomize the order of the data points, right? And if you use a K-fold cross-validation library from scikit-learn or whatever it does for you automatically, but it's one of the options. So randomize the data points so that they're not contiguous, because maybe these are like, if it's demographic data about people, these are different neighborhoods, right? And they're all actually in order by area code. Then you'd have all these things, right? Because some neighborhoods are very rich and some neighborhoods are not so rich. And you'd have these patterns in whatever data you're having, right? And that pattern is in the real data. And so if you want to predict something, some data points might be harder than others. You want to make sure that you're testing your method and really seeing if it does well at this, regardless of the biases and trends in the data, right? So randomizing the order and then using K-fold cross-validation is kind of your core tool that you should kind of keep coming back to. There's other things you can do. You can also additionally, if your data set is kind of small, right? If you have a very small data set, you can do bootstrap sampling. Bootstrap word will come up again and again. You're essentially sampling with replacement, right? So we're saying that you're going to take some samples out and use them, right? But then you're also going to reuse them, right? So here's your model for training, and you know, you're going to take some data points out and use them. Sampling with replacement says that after you sample it, you put it back every point, right? Which means that this data set always has the same number of points in it. It doesn't change the distribution of your likelihood of hitting any object, but it could mean that you might double count, right? So what would this cause? Right? Might cause bias towards those data points, right? Because if you double count a bunch of data points for a certain neighborhood over many times, then you're going to be biased towards that neighborhood and just be kind of a fluke of how your resampling worked. So good randomization methods and thoughtful analysis of like your data and how it's laid out and how to divide it up is really important, because you want to get rid of some of these accidental errors in data that can occur. So one additional quirk into this to give you your standard tool set for experimental methodology here, for at least for the dividing the data portion, is the validation step. So I was talking about your train, test divisions, how much of your data is being used there, but we also want to have a validation step, because not only do we need to handle biases in the data and randomness and kind of deal with that kind of random luck and different kind of patterns in the data from biasing our models, we also want to look at the parameters of the models that we're using, right? So k-nearest neighbors is one we're going to talk about in a little while, and it's very simple at its core. So you have a bunch of data points, and you say let's say that we've been told that these data points are in one class A, and these data points are another class B, and these data points are another class C. Then you ask which class does, whoa, that's not good, does the laser belong to? That should not happen. My computer is getting confused. Okay, there we go. Which model should this point X belong to? And K nearest neighbor says you should use the nearest K points around it. And I should use a different color than that so you can actually see it. Let's use yellow, purple, orange. Orange may not be that much visible given the red, so I apologize. You'd come up with a neighborhood around the data point, which is kind of the meaningful neighborhood, and ignore that one. And you'd count all the points in the neighborhood, right? And so if it's got, 2 neighbors that are A and 3 neighbors that are B and no neighbors that are C, maybe 1, then we'd say, oh, it's A, because that's the one that has the most neighbors of, right? So there's these things you can adjust. But K here, which determines how many neighbors you're going to look at, so you look at the 6 nearest neighbors, is important, right? So here we had, did I say 6? We're going to have 6 neighbors, right? This parameter is really important, and it affects how the whole thing works, right? So you might want to try out different values of K to make sure that it actually works. But if you do that without doing it the right way, then you're going to bias your data and basically beg the question and say, oh, I've picked this number, so it must be good, but you've essentially trained on the data you were testing on, tested on the data you were training on and cheated. It's all to avoid cheating, really, in a sense, that you don't want to give your answer a lot more confidence than it deserves by knowing the answer ahead of time. And so when we do train test validation, we're basically just dividing it up into multiple parts, and a common way to do this would be something like 70% for training, 10% for validation, and 20% for testing, right? With deep learning models these days, they usually just want as much data as possible, so maybe use less and less, but it really depends on your data and its complexity, right? And this is percent, all of this is percent. And so the idea is you use the validation set first to determine the right value for this, right? So use some small part of the data, you try out a bunch of different numbers and see which one works, and really play around, try a number, see it, resample, and do all that. Essentially play until you get this right number. And then using the K you have, whatever the value is, then you insert that in and you train most of your data on that K with the K that you fixed, right? And then the testing is data that you've never used before in any other of these scenarios, and that lets you determine whether it's good or bad, right? It's really important, though, that the idea that the test set is never used during training, right? And the validation set is not used, not reused for testing, because it's already kind of worked in there, even though you're not using it in the training data, it's still biased because it's influential. It's helped you choose that parameter. So you already know that it works well on that number. So testing it on that number doesn't help much because you've already picked it. That's why you picked K equals 6, because it worked good on this data set. And then you trained with K equals 6 on 1,000,000 data points, and you tested on 100,000 data points, but you don't want to reuse any of those. This is to help people trust your results.